Since the lambda calculus gives us functions and booleans and numbers and pairs from which we can build records, it looks like we have in principle a pretty complete language here. In fact, we do have a complete language in the sense of Turing complete, but to make sure that it's Turing complete, we need to double check that we can write loops or equivalently recursive functions. And the way you do that in the lambda calculus is not so obvious, so I'm going to spend some time working through that encoding. As we look at recursive functions, I'm going to use everyone's favorite recursive function. This is the factorial function, which takes an n. If n is 0, it returns 1. Otherwise, it recurs with n minus 1. And here I'm writing it in Plait using the local form. So local form lets me use fac in the body here, but also, and crucially, when we have a local definition, that definition can see itself. The recursive function works because it can see its own binding to call itself. Now, we haven't been using local so much lately as let. There's an intermediate form in letrec, in Plait, called letrec. Letrec, this behaves the same as the local form before, but it looks more like the syntax of let. The difference is between let and letrec, the difference is that we can still see in the definition of fac, it can see itself. In contrast, if we tried to write this with just let, the problem is that let makes this fac binding available in the body, but it does not make it available here on the right-hand side. Right? Let first evaluates the right-hand side, then binds the name fac, and then calls it. Or if you're thinking about the lambda expansion of this, then fac is an argument, is the formal argument name to a lambda. We're passing this lambda as that actual argument, so we're not actually in the function yet here, and we can't see the fac. So that's the problem. If we could express the factorial function using just let, we would be done, but we need something like letrec instead. Right? So our goal is going to be to implement letrec as syntactic sugar for curly. And we've seen that it's not just as simple as let. Instead, I'm going to have to break it down into 3 steps. So first step, we're going to implement fac in just Plait notation, but without using letrec or local. Right? And once we've done that, then we'll go a little further and we'll rearrange our encoding so that we isolate the right-hand side. That is, we isolate the part that we wanted to put on the right-hand side of letrec, which would look something like this, right, in curly notation, right, with the recursive reference to fac that is the troublesome part here. But if we can isolate this, then we can have a parse transformation that picks up this right-hand side and drops it in the right place in our encoding and gives us recursion out of it. I'd like to warn you a little bit up front that you may find these steps actually difficult. I mean, not the individual steps. It'll be clear how we go from this shade of blue to this shade of blue to some beige to some brown. Each of those individual steps should be fairly easy to follow. But the particular steps that we're taking, why we're following those particular shades, and how it adds up to this final big picture, that may end up being a little mysterious. And that's okay. Just want you to know up front it'll be all right as long as you make it all the way to the big picture at the end and understand that final result.